Okay, we're going to talk about complex numbers so that we can start dealing with these imaginary roots that we're ending up with in some of our polynomials. So I'm going to go over the real basic things about complex numbers. We'll revisit these later when we learn some more trig. But for right now, we just want to know the basics of what we can and can't do with them. And then I'll show you kind of when we get complex roots, kind of where they come from and what to do with those and how they occur. So complex numbers is the broad field of numbers that include imaginary numbers. So if you remember the different types of numbers, we have, natural numbers, which are the counting numbers. Then there's whole numbers, which is just the natural with the added one of 0. Then there's integers, which are positive and negative numbers. And then we get into rational numbers, which include all of the integers plus anything that can be described as a fraction. Then there's real numbers, which include rational numbers and irrational numbers. So irrational numbers are the ones that can't be expressed as a fraction. All of those numbers, all the real ones, are also contained in the complex numbers. So complex talks about not only imaginary, but real and imaginary. So if you're dealing with real and imaginary numbers, you're dealing with complex numbers. So this is pretty much all of the numbers that we can talk about. Okay, they're either real or imaginary. All of those are contained in complex numbers. The imaginary ones all come from this fact. The square root of -1 is defined as being I. So before there were imaginary numbers, mathematicians were seeing that, sometimes I get this square root of -1, and they got sick of just saying, well, that means nothing, it doesn't exist. And they made up this I, this letter I, and they said, well, that's what the square root of -1 is going to be. Now we can actually do some stuff with these imaginary numbers and see if they have special properties. So if I know that the square root of -1 is I, if I square I, that's the same as squaring the square root of -1, which leaves just -1. So I cubed, okay, would be the same as square root of -1 times the square root of -1 times the square root of -1. Well, two of these, okay, so let's say these first two. Oops, I didn't want to erase those. But those first two are going to turn into just -1. And then I've got the square root of -1, which is I. So really, I cubed is just -I. I to the fourth, I'm going to have two sets of squares. So I squared times I squared. Both of these equal -1. So -1 times -1 equals 1. So I to the fourth is 1. I to the fifth is going to circle all back. So I'd have I squared, I. Well, this turns into -1, -1. So that's 1I. So this just equals I. And you're going to get this repeating pattern. Okay, so every multiple of 4 power on I is going to be 1. Okay, and then it's just kind of repeat. So if I wanted like I to the 33rd, if I want to know what that was. Well, I know this is I to the 32nd times I. I to the 32nd is a multiple of 4. So this is going to turn into 1, and this is going to turn into I. So then I've just got I. Okay, so if I have I to the, pick some other random number, 55th. Okay, so I want to think of what's the closest power of 4 that's to 55. And that would be 52. So this is I to the 52 times I cubed. I to the 52, that's a multiple of 4. So this just turns to 1. I cubed. I know is -I. So this all just equals -I. So if you got I to a power, it's either I, -1, -I, or 1. All right, here's standard form for complex numbers. You've got A, which is your real part. And then you've got BI, which is your imaginary. Okay, all numbers can be expressed in this form because, like I said, real and imaginary numbers are all contained in these complex numbers. So if I just want to express 3 in complex form, it'd be 3, my real part, plus 0 imaginary parts. Okay, if I want to express 2i, it'd be 0 real parts and 2 imaginary parts. So for operations, we're going to treat I as a variable until we get a power on it. Once we get a power on it, we're going to go back and use these rules for i's to powers to change it up. So let's start with subtracting. So I'm going to subtract these. So I'm taking 2 minus, or 2 plus 3i minus, I'm going to distribute this minus, so it's minus 4 plus 6i. I'm going to combine like terms. So 2 and negative 4, 3i and 6i, this is 9i, and that would be my answer. When we multiply, we're going to do the same thing that we do when we multiply any other time. 1 times 2 is 2. 1 times 4i is 4i. Negative 7 times 2 is negative 14i. Negative 7 times positive 4. So negative 7i times 4i is negative 28i squared. There I've got a power on I. I squared is really negative 1. I'm going to rewrite this. So 4i minus 14i is going to be actually negative 10i. This turns into negative 28 times negative 1, which is plus 28. And I can combine like terms here to get 30 minus 10i. You should always only have 2 parts. Okay, it should always break down into some number in standard form, where you have a real part and imaginary part. Okay, so these imaginary numbers clearly come from when we square root negative numbers. So if I want to add these together, up until now we didn't really have a way to add them together. But now that I can introduce I can actually add these together. So square root of 4 is 2, square root of negative 1, okay, because really this is the square root of negative 1 times 4. Okay, so I can break that square root up and give it to both ones. So the square root of 4 is 2, square root of negative 1 is just I, and this would be the square root of 9 is 3, the square root of 1, negative 1 is I, so this really equals 5i. So if I change that back into radical form, the square root of negative 4 plus the square root of negative 9 is really the square root of negative 25. Square root of negative 25 gives me 5i. So you can go back and forth. Usually we just leave it as 5i because we don't want to have negatives inside there. But I just wanted to show you the relationship here. So now we can solve our polynomials if they have imaginary roots. So if I've got this expression, okay, this is quadratic, so I need everything on one side. So I'm going to subtract that x over. This is not factorable, so I'm going to either complete the square or use a quadratic formula. I'm going to complete the square because I've found that nice, easy way to do it. So negative b over 2a is going to be one part of my, that's going to be the x part of my vertex. So I'm going to have negative negative 1, which is 1, over 2 times 10, which is 20. That's the x coordinate of my vertex. If I put this in for x, I'll get the y coordinate. So 1 over 20 squared is 1 over 400, times 10 is 1 over 40, plus 9. 9 would be 360 40ths. So I get 361 over 40. This is my vertex, so my vertex form would be keep the same a, so 10x minus the x coordinate of my vertex squared plus the y-coordinate of my vertex. Oh, I forgot to put this part in. So this isn't right. So I have 1/40th here minus 1/20th, which would be 2/40ths. So I subtract 2/40ths of this, which would be negative 1/40th, and then add my 360. So really it's 359/40ths. Okay, now to get my roots, I'm going to set this equal to 0. Subtract this over, so I get negative 359/40. Divide by 10, which is going to give me, just add a 0 onto here. Square root it. Okay, if I square root this, the square root of 359 is going to give me a decimal. Square root of 400, though, is 20, and the square root of negative 1 is I. So I'm going to have square root of 359, which I need to break down. And that breaks down into nothing really. I think that's prime. Because they don't add up to 3, that it's not even. It doesn't end in 5 and 0. It's not divisible by 7. Okay, so that's prime, so I'm just going to leave it. So I get the square root of 359 with an I in front from the negative over 20 plus or minus because I square rooted. And then I've got to add my 1/20th. Okay, so there's my two roots in their standard form. Here's my real part, here's my imaginary part. If we have numbers that aren't in standard form, we want to turn them into, you're going to see some familiar tools that we use. Basically, I comes from our square roots. So a lot of the tricks that we use for square roots are going to work for I also. So we don't want I in the bottom. Okay, we want a standard form for this. So we need to know what number is in front of I. Right now we don't have a number in front of I. We have a number on top of I. So I'm going to multiply the top and bottom by I. So that gives me negative 5I over 2I squared. I squared is negative 1. So this is really negative 5I over negative 2. Negatives cancel and I get 5/2 I. So that's standard form now. So I've got 0 plus my I term. Here, I don't want I on the bottom because that's not standard form. So I'm going to use the same trick that we use for square roots. I'm going to multiply by the conjugate. Okay, which is like the completed half of its difference of squares. So I just change it to a plus and multiply this out. So on the top I'm going to get 3 plus 3I over. On the bottom I'm going to get 1. Okay, plus I minus I, they cancel. Minus I squared, which is really minus negative 1, which is plus 1, so I get a 2 on the bottom. So in standard form this would be 3/2 plus 3/2 I. Last thing we need to know is that when we do get these roots, if you notice, when I had these roots here, what I really have is I have these two roots. Okay, I have the plus version of this, and then I have the minus version. Okay, this is always the case. If you have one complex root or one imaginary root, the other one is going to be its conjugate. So you're just going to change the sign between the real and imaginary part to get the other one. So if 2 plus I is a root, then so is 2 minus I. So we can use this to help us find all our roots if we know one. Okay, so if this is a root, and this is a complex, so maybe it'll help if I put the 1/5 in there. This is 2/5 plus square root of 2 over 5i. So this is one root. If this is a root, then so is its conjugate. So just change the plus to a minus. So just by knowing one root, I know one more. Okay, because this one's imaginary, so I know this one is also going to be a root. So I can use this to help divide these out. I can combine these to divide them out. So if this is a root, that really means that my factor is going to be x minus this root. So I'm going to have x minus this one. Okay, so that's going to be a factor of this. The other factor is going to be when I take x minus this one. So minus negative 2/5 minus square root of 2 over 5i. So these are roots. So if I want to divide them out, I'm going to multiply these together. So I do one division, plus it's going to be almost impossible to divide with the I in there. So we want to get rid of that. And when we multiply our conjugate pairs together, which is what we were basically doing down here on this last simplifying, we multiplied our conjugate pairs. We end up with just a real number on the bottom. Okay, when you multiply conjugate pairs, you should end up with a real number. So when I multiply these two factors together, all the i's are going to end up going away. So let's look at how that happens. So x times x is x squared. X times this term is going to be negative this thing times x. Okay, then I'll multiply these, so I'm going to have negative this thing times x. Then I'm going to multiply these two things together, so I'm going to write that kind of on the side over here. Okay, now I've got a difference of squares here. Okay, so I know that the form that this comes from is a squared minus b squared. Okay, so my a is negative 2 over 5. My b is square root of 2 over 5i. So if I just square those and put a minus between them, that's what I'm going to get for my last term here. Okay, so negative 2/5 squared is 4/25. This thing squared, I'm going to have square root of 2 squared, which is 2. 5 squared is 25 on the bottom. I squared is negative 1, which will turn this positive. So really I'm getting 6/25. If you did it out the long way, you would get this same thing. Okay, and it's positive, and it's negative times negative here, so I should get positive. You should always have positive here. Now let's simplify this inside part here. I'm going to distribute my x and my negative signs in. So I'm going to have positive 2/5 x, positive square root of 2 over 5 ix. Okay, I'm going to distribute my negative and my x here. So I'm going to get positive 2/5 x minus square root of 2 over 5 ix. These two terms are exact opposites, so they'll go away. And I'm left with 2/5 x plus 2/5 x. So I've got 2x squared plus 4/5 x plus 6/25. And that's what I want to divide out of my starting polynomial here. Okay, so let's move this down and give me a little more room. Okay, so I'm going to divide this out. So first I'm going to multiply by 25. That's going to give me, or actually 25x. That's going to give me 25x cubed. 25, okay, that's really 5 times 5, so that's going to cancel this 5 out here and just leave 4 and a 5 on the top. So it's going to be 20x squared. 25s will cancel here and leave me with just 6x. Okay, and then we're subtracting all these. So these cancel. This turns into negative 75x squared. This turns into negative 60x. And then I bring the 18 down. So now I need to multiply by negative 75. So that gives me negative 75x squared. Okay, this is 5 times 5 times 3. So the 5 will cancel and leaving 15. 4 times 15 is 60. Here, this is 25 times 3. So the 25 will cancel, leave 3, so I get 18. And then when I subtract these away, I get a remainder of 0, which I should because I knew that I had 2 factors of it. So that means that in order to get my last root, I'm just going to set this answer equal to 0. So I get 25x equals 75, x equals 3. So I've got that root and my 2 complex roots here. Okay, so this is pretty complex, pretty complicated compared to some of the starting ones that you guys are going to have when you start finding imaginary roots. But there's a whole assignment just on complex numbers, and you should be well prepared to do that at this point.